All right, everybody, I think I'm going to get started. Welcome. It feels like the first day of class, but it's actually the second week of class already. I am Dr. Annan. I've been here at Cal State Fullerton for a long time, and almost every single semester I teach this class. Why is it? It's because it's basically my favorite class. I love teaching the class, and you're going to see why pretty quickly on. For one thing, the class just kind of gets better and better as we go along. Like the big punchline, the climax of Math 2 PPP is really at the end. So there's always something to be building towards, which makes it exciting, makes it fun. So I'd be very much looking forward to that. I do want to thank you for your patience with me last week. I was still traveling. I had some issues. I actually got back just 2 days ago. Drove in towards my office just on Sunday, and I'm still getting settled. I spend my summers in the mountains in Colorado. I'm a mountaineer, climber type of guy. I climbed hundreds of mountains, mostly in Colorado, but I've actually climbed mountains all around the world. And sometimes those adventures take me very far from the cell phones and internet access and stuff. So it's kind of hard to teach a class when you're kind of back in the backcountry for so long. So I do appreciate your patience in watching those videos. I did have a chance to look at the notes that you all took. For the most part, everybody did a great job. A few little snags with kind of following the directions about submitting in one file with all the pages in the correct order. But we're going to get over that issue, I'm sure, very quickly. So anyway, I do appreciate that. That allowed us to kind of keep up to schedule with the material and gave me a chance to kind of get back here on schedule. What we did fall behind on a little bit is the homework, because normally I would have asked you to turn something in last week, I think. But I felt it wasn't really fair to do that since I wasn't easy to get a hold of, and I didn't want to ask you to just figure it all out on your own without a chance to ask me anything. We do have an assignment due tonight, and we're going to be catching up because there's also one due on Thursday. We're going to try to make up for, well, it's really my fault being gone last week. So just keep that in mind. I do have a ton of office hours, especially on Tuesdays and Thursdays. I do have another class right after this class. So the best time to catch me is either going to be in the morning, like before I start teaching, so like about 8:45 till 9:45, or after my second class, which is going to be over by 5:30. So I'll be downstairs starting at 5:30 until 7, and I'll be back downstairs again between 8:30 and 10 tonight. Your homework is due at 11:59. Also, you see on the sideboard, I have a place for you. If you ever come in on a day that homework is due, and you're like, oh, I'd like to have Dr. Annan take a look at this question with me or with us, you can just write down a problem number on the board over there, and I'll be happy to, if I have time, I'll be happy to try to take a little bit of time to look at it with you. We will always take a 10-minute break in the middle of class, so if you were thinking you wanted to put some problems up over there, you'll have a chance to do that when we take a break about halfway through the class today. So I'm just going through my list here of things I need to talk about. And yeah, there's also an assignment due on Thursday, also due at 11:59. So we'll kind of repeat the same routine on Thursday with the second set of homework problems. Okay, with that in mind, oh, and also whenever you walk in here, I will always try to have a summary of the previous, like the highlights of the previous class on the board already, so that if you wanted to just do a quick review or write these down, it's kind of good to have the highlights. Like usually students find out a few weeks into the semester that, oh, it might have been good if I was writing those down, because it is a nice little bullet point summary. So I'll go over this in just a few minutes. I'll review what this is. I am going to cover it up for a second though, because I want to pull this screen down and turn on my screen, because we are actually very lucky this semester. I have 2 different people helping me with teaching this class. One is a person who's going to be grading for me. So they're going to help grade your homework assignments and give you feedback. We'll be able to get much more feedback that way. And then another person that we have helping us is actually here in class with us. And that is a person who's going to be leading this supplemental instruction class that goes along with Math 250B. So this is kind of like optional thing that you can add on. And the person running this class, we're very lucky. First of all, he's coming to my lectures, so he knows exactly what I'm covering, as opposed to students maybe with different professors. So he'll know exactly what I'm covering. And also he's a former student from this class who took it with me, and he happened to ace it. So I think we're in good hands with Janda, and Janda's here. He's going to come up and make a quick announcement about this SI class and tell you when and where and why you should sign up.
All right, thank you, Professor Hammond. Sure. Hi, everyone. My name is Shanda Wang. This is my 4th year as a computer science major student. It's also my 3rd semester of being a SI leader. In fact, 3 semesters ago, I was here at this very same room where my Professor Anna was my 250B professor. And I was very fortunate because Professor Anna right here is the best of the best professor right here. And I'm truly amazed to be enlightened by him. So thank you for that, and good to be back here again. So what is SI? SI is a 1-unit course where students get to have extra practice and review through peer collaboration. Statistically, students that go to SI consistently generally have 1 letter grade higher than those who don't go to. So I think that's a pretty good deal for going to SI. And on top of that, SI is free. It's already part of tuition, so you don't need to worry about any fee payment and that kind of stuff. So yeah. And again, SI is for everyone, whether someone trying to get an A or just hoping to pass the course. SI can help with those goals. You don't need to be enrolled in this class, even though 251B is a 1-unit course, but you can still just come by and drop in, even if you're not enrolled. So once my session starts is basically it starts right after this class ends. So 4 p.m. to 5:15 p.m. on every Tuesday and Thursdays at this building, room 187D. So is there any questions or doubts?
It's kind of good timing because from 4 o'clock to 5:15, I'm not available. That's when I have to teach another class. So Janda's going to be doing this SI session in that meantime, and he can give you some different insights and points of view on the material. And then you can come bug me in office hours after that later on in the day as well. So there'll be lots of opportunity to get help with everything. So thanks, Janda, for your assistance with the class. Let's give him a hand. I think I like the fact that you can just drop in, right? So you don't have to have been going every day for the whole semester. It could be, oh, gee, the exam's coming up in another week or so. Maybe I should get some extra practice. And Janda is going to have some good practice problems for you to do. Taking an active role in your learning is always the best way, I think, to master the material. So highly recommend that. So great. It's awesome that we have Janda helping us out this semester. Okay. Yeah, I'll go ahead and put this screen back up again, because in case some of you do want to jot down this summary here, you can certainly do that while I'm kind of talking today. And yeah, I see people taking pictures and you're recording the lectures or whatever, that's fine. Notice I am up here with my laptop. I'm going to be recording all of these classes, and then there is a place in Canvas where I'll be posting my lectures. Why do I do this? Well, it's not so that you can just stay home and not come to class because you're just going to watch it on Canvas later. No, no, no. You need to be here. But sometimes students 3 weeks later, they want to go back and review something. Or maybe they missed some notes. Or maybe there really was an emergency and somebody did have to miss class or part of a class. By all means, I'm going to make these videos available, and you can take a look in Canvas for those class lectures. I'll show you in Canvas where I'll be keeping those in a little while. Right. So before we actually do any math today, I want to take a minute, if I can find a pen here. I'd like to take a minute and go through the class roster. Several of you have already stopped by to say hello, either in Zoom or in person during my office hours. Great thing to do. In fact, I'd like everybody to do that. I will learn your names much better if I sort of have one or two of you at a time kind of floating in and out of my office rather than trying to, learn 30 something names right now. But I still would like to just go through this partially because I have a fairly big waiting list for the class, and we need to try to get this all sorted out this week because I think the ad deadline is like about a week from now. So I'm gonna go through and just feel free to correct me if I pronounce your name incorrectly. I'm gonna try my best. I am from Nebraska originally, so everybody's name in Nebraska has like one syllable and it's like easy to pronounce. So sometimes I get challenged by these things, but I'm gonna do my best. So I'm gonna go through in alphabetical order here. Is Zaid here? Zaid. Okay. Yeah. And again, just correct me if I'm saying thing properly. Adan here. Gotcha. Thank you. Andrew Aro. Thank you, Andrew. Kian or Keon. Okay. Sasha. And is Kim Broderson here? Okay. How about Angelo Carney? Thanks, Angelo. Maxwell, there he is. And Angelina Shin. No Angelina today. Darren Dale. Gotcha, Darren. Thank you. Dorsa. Thank you, Dorsa. Bryce Flores. Got you right here. Chris Gomez. Thanks, Chris. Tony. Thank you, Tony. Alex. There he is, right? Yep. I recognize you from my Zoom little screen, so at least the video is good enough for that. Is Leo here? Thanks, Leo. How about Jordan? Thank you, Jordan. Destina? Am I saying it right?
Yeah.
I got lucky. Jesse Jones. Thanks, Jesse. And Matthew introduced himself. There he is. Okay, thanks. And Liam. There he is. Mason. Thank you, Mason. Jesus. Saw him somewhere. There he is. Gotcha. Marcus. Thanks, Marcus. Kimberly. Right. David Morales. Is David here? Just in my office an hour ago. I don't think he's here now. Okay. Taylor. Thanks, Taylor. Imtinan.
Here.
Did I say it right?
Yes, you did. Thank you.
Perfect. And Matthew. Gotcha. Trung Nguyen. Trung is not here. On. Okay. Riley. And Nick Ramirez. Let's see, Yordi, Adrian, Yordi, am I saying it right?
Yeah.
Okay, perfect, thanks. And I don't think Angelica Sirna is here, is that right? Okay. Evan, somewhere, there he is. Laura Suarez.
Here.
Thank you, Laura. Bruce Tran. Bruce, and how about Milton? Is Milton here? Gotcha, thank you, Milton. Is there anybody here who I didn't just call off? I get everybody's name here. Okay. Okay. Yeah, so there's several of you on the waiting list. I see Angelo, Leo, Matthew, Jesus, David, Matthew again, Angelica, and Bruce. So there's actually 9 people on the waiting list, but there's actually only 33 of you here in total right now, which is kind of, so there's some people missing. So let me work on sorting it out. Technically, my roster is a little bit more open in the morning. I have a 10 o'clock class also, so there is some possibility of maybe stretching this a little bit. I can't go over the class limit. Like there's only so many chairs in here, and one time I tried to like just go around the back of the math department and just like add a couple people, because I normally I would like to add people if I can, but then they found out that I was like going over the fire limit, and I got this email saying, oh, you've been here for 20 years, you should know better than that. And I kind of got in trouble and they wouldn't let me do it. So it was like not up to me. So I'm doing my best to add as many people as I can. And I know some of you are really working hard and trying to get in the class and everything. I'll do the best that I can. Hi there. Can you tell me your name?
Kim Broderson.
Ferguson?
Broderson.
Ah, yes. Okay, gotcha. Thank you. Okay, perfect. Okay, yeah, so what we need to try to do, as far as those of you trying to get added to the class, I have to send, the way it works now, you cannot add any longer through the portal, through the class roster or anything. You can just, basically, you're sitting on the waiting list at this point, that nothing will happen with that. I have to add you myself. So I have to send an email to the math office and just say, yes, could you please enroll these people? And then, as I just explained, they will check and make sure there's actually room in the class to add you. And then if possible, I would try to do that. So let's try to get that settled this week. If we get to Thursday or Friday and you're still kind of in limbo, wondering about things, make sure you reach out to me, because I do have a lot of people kind of shuffling around. And it might be possible that I can add you to my other section instead of this one or something like that. We'll see what's possible. Hopefully by the end of the week, we can get that all squared away. I think next Monday or Tuesday is the date you need to add by, so that it's simple. Once that add date passes, then you suddenly need like 5 signatures and you have to go pay an extra fee and all this stuff. We don't want to get into all that. So let's see if we can get it squared away this week. Okay. Any questions before we get started today? Yes.
Also, students who say hello to you in the Zoom are the students you had previously.
Pardon?
Also, students who say hello to you, who you had them from the past.
I've had students, new students, old students, everybody stopping by. So
Oh.
everybody should try to stop by. I think it's in my syllabus. I'll learn your names better, and I'm also gonna drop your lowest, what did I say, 2 homeworks or something like that?
You'll drop
Homework and
the-
a quiz. It's in the
homework?
syllabus, so check it out, but you gotta do that within these first 2 or 3 more weeks. I think it's September 17th is the date that I put down.
Oh,
You know
you,
what, several of you have already done it. I've been keeping track. So if you've been in my Zoom or in person to my office, I've jotted you down as stopping by. So plenty of time to do that if you haven't been able to do it already.
oh, so you drop your lowest 2, 3 homeworks.
I think it's 2. I think I have that in the syllabus.
Oh.
So just check the syllabus.
All right.
Okay, I'm gonna go ahead, I think, and get started here. I always like to begin class by recapping where we left off, and in this case, where we left off was with some videos. I remember that in the videos that you guys watched for me last week, I tried to motivate this topic a little bit, right? I gave some applications of differential equations, things like Newton's law of cooling, as well as like these chemicals mixing into a tank type kind of thing. So we had a little motivation for the subject of differential equations, and then, of course, the real thing we want to do is learn how to solve them, right? And so if you take any differential equations class at any university and you want to know what are the types of differential equations that they're going to show you, most likely everybody is going to show you these 2 types of differential equations first. Why is that? Oh, it's because they're the easiest to solve, and they're the ones that come up the most often in the real world, right? So you could talk to your engineering friends about differential equations that they might be seeing in their classes. Most of those differential equations, right, they're going to be separable or linear. Separable or linear. So I have videos for you to watch about how to solve these differential equations. And so just a quick reminder, right, a separable differential equation here, well, it's exactly what the name implies. We're going to separate the variables onto opposite sides of the equal sign. So everything that depends only on X would be on one side. Everything depending only on Y is on the other side. Now, it may not be given to you separated in the first place. This means we must sometimes have to do some algebra to try to manipulate the expression to get all of the variables separated. And in fact, I consider that maybe to be the hard part, right? Getting it separated. So we have to sometimes work a little bit at doing that. And in the videos that you watched last week, I showed some examples of that, okay? But once you get it separated, It's a very easy process, right, to solve the differential equation. All we have to do is try to integrate both sides and then solve explicitly for y. Now, I say if possible, this is because sometimes you cannot actually isolate y, like you can't just get y equals something, right? So if that's the case, then we might have to settle for an implicit solution to the differential equation. But of course, the goal, if possible, is the best thing is going to be to explicitly solve it for y, right? So that's the idea. And actually, this is going to be practiced on the homework you're going to be working on for Thursday. So anyhow, that's a separable differential equation. Newton's law of cooling. That's a great example of a separable differential equation. And then the second type of differential equation that is very, very common is the so-called linear differential equation here. And I'm going to put a box here. The form of a linear differential equation is what you see on the board right here. Y prime plus some function of x, it could be anything, times y, equals some other function of x on the right-hand side, which I'm going to be calling q of x. Now, once more, the equation may not be given in that form initially. So one of the challenges is, okay, maybe we're going to have to do some manipulating of the equation to get it into this form. For example, if there was something in front of this y prime here, in the very first term, that's not an acceptable form to match this box. And so we would need to first, divide down by whatever was the coefficient of that y prime to get it into this form, you see. Right. So there can be some work involved in doing that. But if we can get it into this form, then it is linear. And in my videos that you watched last week, I basically derived the procedure for solving a linear differential equation, first order linear differential equation. And we found out that it involves something called an integrating factor. I call this I of x, and this actually should probably, anytime I'm putting something into a box, guys, probably means you should know it. You should be maybe making flashcards or at least highlighting in your notes somewhere, because these are things I'm going to expect you to know, right? I'm not going to be, handing out cheat sheets with the forms of linear and integrating factors and so on. Is something you're going to need to know. That, especially something this well-known and popular and important, people need to just know this stuff cold. So make sure that you're working on that periodically as we go forward. But here's the formula. The integrating factor is e raised to the power of whatever that p of x function was. Okay, p of x being this coefficient of y in the original form of the differential equation. And so we do e to the integral of p of x dx. That's the integrating factor. And I won't go through the whole derivation again, but if you remember from my videos, what ends up happening is when you multiply the linear differential equation through by this integrating factor, you end up getting a derivative of a product on the left side. And it's exactly the derivative of the integrating factor times the unknown function y, right? Which is what you're ultimately hoping to solve for. And on the right-hand side, you've just taken q of x and multiplied it by the integrating factor. So again, you can just memorize this step here. I guess I can put a box on that one too. That one's a little easier to actually derive it if you wanted to, but I prefer to just kind of remember the process that you're going to have there. Once you've done that, the only thing left to do is to solve explicitly for y. And this time you will be able to do that fully. You'll integrate both sides, which will get rid of this derivative. And then once you have I times y, you can solve for y if you just simply divide through by I. So that's kind of just a robotic process that you have to use at that point to get the y, which is the solution to your differential equation. Okay, so in those videos from last week, I went over why these processes work, how they work, and there were some examples there, as well as the physical real world problems that use these methods here. So I just wanted to recap it. I will do that It's always good, guys, on these classes that only meet twice a week, especially on a Tuesday, to take a look over your notes before you come in here, because otherwise, if you're just kind of coming in cold, right, it can be hard to keep up a little bit sometimes. There's a lot to cover in this class, I have to tell you. I was talking to somebody yesterday about this class, actually, and a former student of mine. And I was saying, the students, they've told me it's a lot of homework, and it's a lot for a 4-unit course. There's so much material and everything. And I said, yeah, tell me about it. Like, I'm teaching the class. I'll be breaking a pretty big sweat myself, just trying to cover everything and get through the material. It is what it is. It's the nature of the class, and you really have to have this attitude about it, that the payoff of the hard work that you're going to do is massive. Like, you probably felt like you grew a little bit when you went from Calc 1 to Calc 2, and then maybe you grew a little bit more from Calc 2 to Calc 3. When you go from Calc 3 to the end of this class, right, after learning 15 weeks of differential equations and linear algebra, it is a huge step up. That's a good thing and a bad thing. It's kind of, in the moment, it's a little daunting. But in the long run, when you look back 4 months from now of sort of where you are right now, compared to where you're going to be in terms of your mathematical maturity and your exposure to kind of like what mathematicians do and what math is all about, you will have made huge strides if you put in the work for it. So you will get your money's worth for your tuition. You'll notice on the homework assignments, for example, you know how I have, you probably already saw this, the required problems and the recommended problems. It used to be all of those problems were required. I think I'm getting soft in my old age. What's happened is I had enough people tell me, yeah, it's just kind of too much. So I cut back a little bit. I've decided to kind of take some of those required problems and shift them down to recommended problems. But this former student that I was talking to yesterday, he actually said, yeah, it's a lot of problems, but every single problem, there was something to learn from it, right? It wasn't like I was asking 10 problems of the same thing and just making people like slave through the same thing again and again. Every problem had something to take away from it. So that's why I was so hesitant to like pull anything off of that required list. But even with just the required list now, it still is going to be a lot of work. Like, there's going to be 2 homework assignments pretty regularly each week. And so you're really going to have to stay on the ball. You cannot just kind of come Tuesday and Thursday and then, oh, Thursday afternoon, I'm going to just check out until next week, right? So during that 4-day interval from one class to the next, you do need to stay engaged with the material. That's why I have so many office hours on Thursdays, Sundays, Mondays, Tuesdays, right? I try my best to be around so that I try to fill in those gaps a little bit. So I'm not trying to scare anybody about anything. I'm just trying to hopefully set the mindset that you have to have with this. It's not my syllabus. Like, I didn't design the class, right? The department basically says, here's what we need the students to learn. By the time they've come out of 250B, and it's just my job to figure out how to make it all work. So I do my best, and I hope that you guys will be able to do that as well. So that's kind of where my thoughts are about the class. Okay, what I'd like to do right now, guys, is I would actually like to cover one more new section. And it is section 1.8 in the book. So we are going to finish this. This is actually the last section from chapter 1 that we're going to cover. And this is called change of variables. Change of variables. So now what is this all about? The idea here, guys, is that, of course, there are lots of differential equations out there that are not separable and not linear, right? But we still like to solve them. So here's a trick. Here's an idea. And it's the same idea you did when you learned how to do integration. Maybe you have an integral that you don't know how to solve, but if you do a u substitution, right, you can convert it into something that you already know how to solve. We're going to do that here as well. We're going to do something called change of variables, where we take a differential equation that's not separable and not linear and convert it into one of those. So I'm gonna give you two examples of this. I'll call these A and B. And we'll talk about each of them. So the first one is a Bernoulli differential equation. And I'll tell you in a minute what that is. And the second one is something called a homogeneous differential equation of degree 0. Okay, so let's see if I can explain these after I tie my shoes again. The idea here is that we're going to take whatever these equations are, we're going to change the variables that are in those equations, and we're going to convert them. I'll draw little arrows over here. We're going to convert them into something more familiar. It turns out that Bernoulli differential equations always become linear. Okay. And it turns out that homogeneous differential equations of degree 0 always become separable. So by converting the equation through a use of change of variables, we can end up with a differential equation that we already know how to solve. We already learned, and then we could solve that equation instead, and hopefully that'll help us to go back and solve the original equation. So let me tell you what a Bernoulli equation, let's just go through these two things kind of one at a time here. I'll make a definition. So anytime I'm doing that, I'll write DEFN. Stands for definition, and I'll usually underline the word that I'm defining. So I'm going to start with the Bernoulli one. So a Bernoulli differential equation has the form, here we go, y prime plus p of x times y equals q of x times y to the power of n. Now, guys, in this little subsection of today's class, there are going to be 3 important equations that you absolutely have to learn. I'm going to put all 3 of them into a box so you'll know which ones they are. And this is the first one. This is the first one. We need to know the form of a Bernoulli differential equation. Do you see how it looks almost linear? It looks almost linear. Here's the linear form. Y prime plus p of x times y equals q of x. The only difference here is that on the right-hand side, I have y to a power of n. That could be y squared. That could be y cubed. Of course, this is making it not linear, right? If I have a y squared, it's not going to be linear. If I have y cubed, it's not going to be linear. If I have e to the y, it's not going to be linear. If I have 1 over y, it's not going to be linear. If I have the square root of y, it's not going to be linear, right? So any value of n is possible, right? And it makes this thing no longer linear, according to, I think I talked about what a linear equation is last week. Yes, question?
Just divide y from both sides and then kind of turns linear.
Well, I could try to divide through by y to the n, couldn't I, to kind of get rid of that? But of course, then I'm going to be putting those powers of y on these terms. And no matter how you try to cut it, it's not going to be back into this form again yet. So I wish it was that nice. It's good to think about simple ways of addressing these issues, but here we really cannot get away with that. So this is a Bernoulli differential equation. And so to solve this, we are going to use a change of variables, and I'm actually going to use a u to describe what the variables are here. So u is going to be the new variable that I'm going to change to. And here is the formula for it. By the way, this formula that I'm about to write down is going to look like it just sort of fell out of the sky. Like I'm not really going to derive it. This is something that a mathematician way smarter than me and way before I was ever here figured out. And what it is y raised to the power of 1 minus n. So again, I'm not deriving that. And you're maybe sitting there thinking, where is that coming from? Well, the answer is somebody figured this out, that this is the magic trick. And so we're going to employ it right here. This is the change of variables. Notice I put it in a box again. That's because that's another absolutely essential equation that you have to know in this little subsection. Okay. And if we sort of use this change of variables, we can convert our original Bernoulli equation into a linear one. That's what I'm saying up here, right? So in fact, what we're going to get, we will obtain. And I'm going to say here, see videos. That's because I'm not going to derive it right now. I'm going to tell you what we're going to get, which is we're going to get u prime plus the quantity 1 minus n times p of x times u equals the quantity 1 minus n times q of x. And notice I'm going to put a box around this as well. That's because you have to know this equation also in order to be able to do these problems. And I'm going to do an example in a second, but guys, notice 1 minus n that you see here and here is just a number. It's just a number, right? It's just whatever this n was in the original problem, right? That number is going to be transferred here with a 1 minus n on it. And so it's just a number. So actually take a look at this new equation, right? Instead of y prime, it's u prime. And instead of y, it's a u. But notice that the original p of x has just been multiplied by a number. This is almost like a new p of x. It's just been scaled up by some numerical value. It's still a legitimate function of x here. And on the right-hand side, same thing. The original q of x has just been scaled by some number. And so it's a legitimate new q of x, so to speak. But what's really important is there's no u to the n over here. There's no power of u like there was a power of y in the original Bernoulli equation. So somehow this change of variables that magically somebody figured out has helped us to get rid of this u to a power on the right-hand side. And therefore, my friends, this has now been re-expressed in a linear differential equation. Okay. Now, I say see videos, and I say we will obtain this. What this means is that, well, I've taught this class a lot of times, and I used to go through the whole thing. And I would derive everything from going from here, plugging this in, and then deriving this. And of course, it's not that interesting because it's not really the practical side of doing these problems. So what I did one day is I decided to make a video and just like have it as like an outside thing, because I generally am not the type of professor who's just going to hand you formulas without explaining them or without at least giving you an idea why they're true. And so it's not like me to just sort of throw this up on the board without any kind of a justification. So what I do as a compromise in this case is I said, I'll just make a video. And the students who want to watch it, they can. If you don't want to watch it, you don't have to. So in a little while, I'll show you where you can find this video on campus. Actually, it turned out it's only a 3-minute video. So if you're interested in it and want to spend 3 minutes, you hardly have time to finish your popcorn with a movie that short. So, but anyway, I'll try to give you some links to that and show you where you can find that a little bit later on. But this is what you need to know. These 3 boxes, if you know these 3 boxes, you can solve any Bernoulli differential equation. Let's try an example. Let's do an example to practice that. I got to find where I am here in my notes. Oh, it's over here. That's why. So here's an example. Let's solve y prime plus the fraction 2x divided by 1 plus x squared times y equals xy squared. Let's try to solve this differential equation. Now, I should point out that, eventually you guys are going to see all of these types of differential equations scrambled up. You're going to see a Bernoulli one right next to a separable one, right next to a linear one, and so on. And so it's not a bad habit to get into, to just sort of go through the motions and ask yourself, are we sure this is not separable? right? We gotta try our best to split the x's away from the y's here. It's a pretty messy one, right? Usually if you want to separate a differential equation, you're gonna have to use some algebra to get all the x's on one side and all of the y's on the other side. And this doesn't look like easy algebra, right? Even something this simple. So I'm suspicious about this. I don't think I'm gonna be able to separate it. Okay, fair enough. I can easily see that it's not linear. It's not linear because y squared, as we talked in the videos last week, right? You can't have y times y. That doesn't count, it's not allowed. So it's not linear. But of course, when we set it side by side with the form of a Bernoulli equation, it matches up perfectly, right? It matches up perfectly. The p of x would be right here. Yeah, this is p of x in front of the y. And then this x right here, that would be the q of x. And so this is Bernoulli. Let me start my solution here. This is Bernoulli. And can somebody tell me what is the value of n here? The value of n, Matthew. It's the power of y on the right-hand side. I see a y squared right there, so that's exactly right. N equals 2. Guys, if I put something like this on a test and you simply write down, oh, it's Bernoulli with n equals 2, I can already give you partial credit for that, right? That every little thing you write down, even if you're like, I kind of forgot some of the details of this, but if you do know that it's Bernoulli and if you do know the n value, you should write it down because I can help you with that in terms of partial credit. And also, if you want a little more partial credit, you could then write down what the change of variables would be. So u is equal, so now I'm going to go to this one, right? U is equal to y to the 1 minus n, which in this case would be the power of 1 minus 2. And that's really just a -1 exponent, and that's perfectly fine to rewrite that as 1 over y. So u is equal to 1 over y. It's the reciprocal of y, right? These two variables are reciprocals of each other. Okay. Stop me if you have a question. Just make sure I'm making sense, I hope. Okay, so we write down this thing here, right? This is, again, even if you're not quite sure, like maybe you forgot part of the steps you have to do, if you write down as much as you do know, I can give you as much credit as possible for your knowledge of that. So we have that, and then what we're going to obtain then is we obtain a new differential equation, which is u prime plus, now let's watch this, guys. N is equal to 2. If I put 2 everywhere I see the n up here in this boxed formula, notice that I have 1 minus n. That's just -1, right? 1 minus 2. So that's a minus sign. So I'm going to treat that as a -1 times whatever p of x was, which was 2x divided by 1 plus x squared. That's times u. And that equals, on the right-hand side, I have 1 minus 2, which is a minus of whatever the original q of x was, which was just x itself. So I'm picking up these sign changes because of the 1 minus 2 being equal to -1. Is everybody with me? This is now linear. We've changed variables, and in so doing, this Bernoulli differential equation has become a linear one. And I like doing this because now it's a chance to review the linear process, okay? Just be a little careful because we have a new p of x and q of x now, right? The original p of x and q of x that I identified over here have picked up these minus signs. So that when I go to the form of a linear equation and I start thinking about solving the linear differential equation, I have to remember that those minus signs are part of the p of x and q of x. So for example, when I want to do my integrating factor, right? This is e raised to the power of the integral of p of x dx, but I'm talking about the new p of x, not the one that was in the original problem, but the one that has the minus sign in it. So this becomes a minus of the integral of 2x over 1 plus x squared. I'm just going to put the minus sign on the outside of that integral, like so. Does anybody know how to do this integral? So this is e raised to the negative of this integral, which is 2x over 1 plus x squared. Anybody know how to do that integral? Evan?
So, u equals 1 plus x squared, and then du would be 2x.
Exactly. So Evan got it exactly right. See the 1 plus x squared on the bottom? If I just call that u for a second, then notice the numerator is just the derivative of that, right? So the derivative of 1 plus x squared is just 2x. So guys, this is the integral of du over u. Okay, so maybe over here on the side, I'll just write down, we're doing u equals 1 plus x squared. This u, of course, has absolutely nothing to do with the u that I'm using in my change of variables with this section. This is back to the u substitutions from calculus. So this is just e raised to the integral of du over u. Does anybody remember what is the integral of 1 over u du? The natural log of u, right? Actually, it's the natural log of the absolute value of u. I'm going to just go ahead and write that down without showing a huge amount of work here. I should mention, guys, to the extent that I can, I try not to make this a class about like having to go over a bunch of hard integration again, right? It's not the point of the class. It's never going to be my big sticking point. I obviously expect people to be able to do easy integrals. You have to be able to do some simple ones, but you should not be freaking out getting these crazy integrals from 2 semesters ago that use these weird techniques or anything like that. I would try my best not to have too much of that going on. Anyhow, this a couple comments here. First of all, those absolute value bars are actually not really needed here because after all, 1 plus x squared is already positive. So taking the absolute value of something that's already positive really does nothing. So I'm not going to worry about the absolute value bars. The other thing I would like to point out is that normally when you do an indefinite integral, you would typically add a plus c as the constant of integration. But in this theory, we only need to find one acceptable integrating factor. And that means we can just pick a value of c that we would like to pick. And I would always just pick 0. Because after all, if c is 0, then you just don't have to worry about it. So I'm just not even going to bother with the plus c. I'm just going to leave that off. I'll get rid of the absolute value bars too, because we don't need those. Do we know how to simplify this one? Leon.
Want to pick the natural log of the derivative?
The e and the natural log, they kind of cancel, don't they? Because they're inverses of each other. That's exactly right. The only issue, though, is there is a minus sign here in front. So the way that we handle this, and I know that this is just algebra stuff, and I kind of talked about it in the videos as well, but that minus sign can be thrown up as an exponent. This is one of your logarithm properties. And the reason for doing that is so that you can then cancel the exponential function against the logarithm function. And so now you just have the reciprocal of 1 plus x squared. That's your integrating factor. Okay, and so now, it's kind of convenient, I still have this on the board. What happens with this integrating factor is that it ends up as part of a product that you're taking the derivative of. So I'm just going to go straight to that. I take the integrating factor, 1 over 1 plus x squared, times the unknown function. Let's be clear right now, the unknown function is this u here, right? So I'll put u right here. I'm going to take the derivative of that product, yeah? And on the right-hand side of the equation, I have the q of x. Remember, we're talking about the new q of x, which is this one, negative x times the integrating factor, which is 1 over 1 plus x squared. So there's your transformed equation. Again, I'm assuming you've all watched the videos on kind of how this works. It's just this box right here is all I'm doing, except I'm doing it with u rather than with y. Right. Last step is to integrate and solve explicitly, well, for u. Okay, so I'm going to take this thing and integrate both sides. Let's write that down. We're almost done. We're almost done here. We're going to integrate both sides. So 1 over 1 plus x squared times u. When you do an integral, it sort of cancels a derivative because they're kind of like inverse operations, right? And then all I have to do now is integrate on the other side. So I do the integral of negative x over 1 plus x squared dx. actually, that integral is not a whole lot different from the one we just did a few minutes ago right here. There is a little factor of 2 that would be nice. Well, I can put a 2 in if I want, as long as I put a 1/2 outside. Nothing wrong with that. And so what you have here, guys, is 1/2 of the exact same integral we just did a few minutes ago. This integral turned out to be negative, so I put the minus there, of the ln of 1 plus x squared. I won't use absolute value bars this time because again, it's always positive. Okay. And this time, the other thing we have to be clear with this time, my friends, is we do need the plus c. Okay, so I didn't need to put that in the integrating factor, but right now I'm trying to solve for the general solution to this differential equation, and that plus c is no longer sort of optional. Like we have to put it here. Okay, so we have integrated both sides. Is everybody with me? Am I going too fast? I do get excited. It's not that I'm trying to be too fast. I understand it takes a while. I gotta write it all down, take careful notes and pay attention. I just get excited, that's all. So you just have to ask me a question, calms me down, slows me down. Happy to do that anytime. What do I need to do next? Isolate the u. Yeah, here it says solve explicitly for y. So translated to this, it would be solve explicitly for u. So if I do that, I just need to sort of throw this 1 plus x squared over to the other side, right? So let's just do that. So I'm going to write u equals the quantity 1 plus x squared times, and I'm going to get out my big brackets. This is kind of a messy expression, so we'll get out the big boy brackets here and put this whole right-hand side inside of those larger brackets.
Where did 1/2 came from?
This 1/2 was because up here, when we do the u substitution with 1 plus x squared, right, the derivative of that has a 2x dx in it. So this 2, when I replace the x dx, I have to divide by 2.
Oh,
Du over 2.
got it.
Quick question, guys. Is it okay to take this plus c and just kind of throw it out to the right-hand side on the far right? Oh, that is such a popular thing to do. I see it many, many times. No, you cannot do that. We really need to leave it in the brackets. This c should feel the multiplication of the 1 plus x squared, right? Because after all, this 1 plus x squared is multiplying everything that's on the right-hand side of the equation. So I don't want to make an algebraic goof here. Keep those brackets there. You don't really have to simplify stuff too much, guys. I'm not real fussy about that most of the time. So just kind of leave it the way you find it, just like that. And now am I done? I see people saying, no, what do I still need to do, do you suppose? Yeah.
Plug y back in for u.
Exactly. The original problem was involving the unknown function y. And we were solving for y. And right now I have solved for u. So the last thing I need to do is figure out, well, how do I figure out what y is? That's where this comes in. That's where this change of variables step is so critical to write it down, yeah? U and y, they are reciprocals of each other, right? As you can see from here, if I just flip both sides, y is going to be equal to 1 over u. So let's write it down. Y is equal to 1 over the whole entire expression for u, which is the quantity 1 plus x squared times the quantity of negative 1/2 times the natural log of 1 plus x squared plus c. And we just leave everything in the brackets the way we had it before. This would be the final answer. Okay, so always good to circle the final answer. That would be the one. That would be it. Of course, if I had an initial value, right, then instead of this general solution, as we call it, if I had an initial value, I could, of course, try to figure out the actual value of c by using that initial condition. There's a little bit of that in the homework as well, right? So that's kind of the idea there. But we don't have an initial condition here. That's the whole ball of wax. What do you think? Any questions on this method? So I actually like these problems because they force you to kind of keep remembering how to do the linear differential equations. right? At the same time as you're kind of tacking on this powerful technique of change of variables. So Bernoulli differential equations, that's kind of what this is about. By the way, all of this stuff that I'm going over right now, you won't have to really do homework on this section until like 2 more assignments into the future. So I try to keep my lectures ahead of the homework a little bit, so you have some time to kind of soak it up and absorb it a bit. Okay, before we take our little 10-minute break for the day, I would like to talk about how to solve homogeneous differential equations of degree 0 as well, as long as there's no questions so far. Remember, guys, 1, 2, 3 important equations. I would highlight them or I would make flashcards, whatever you need to do because if you have those 3 equations in hand, you can carry out this process every time. I promise it's not that bad. Okay, I'm going to go ahead and start right here again with the part B of this little section. And so for part B, we're looking at homogeneous differential equations of degree 0. Okay, and kind of like I did for the Bernoulli ones, I'm going to start with just what is the definition. So what is the definition of one of these things? Let's write down the definition here. DEFN, the definition. A homogeneous differential equation of degree 0 has the form. Again, I try to underline what I'm defining here. So we're going to look at one more example of changing variables here. What is the form? Well, for this one, we're actually going to get the y prime isolated by itself on the left-hand side of the differential equation. And what goes on the right-hand side is going to be some function. I'm going to call it f of x and y. So this, in theory, this function could be anything, right? It could be some big alphabet soup of x's and y's with every fathomable calculus function you can think of kind of in it. But of course, this isn't the end of the story because, there's got to be some requirement here on this function in order for it to be homogeneous of degree 0. And I'm going to tell you what that is now. This is the key part. This is the critical part, is that this function, f of x and y, cannot just be any old function whatsoever. Rather, it has to have kind of this weird property. And what is the weird property? Well, this function has to have the property that if you go into it and everywhere you see an x, you decide instead to replace that x with x times t. And everywhere you see a y, you decide to replace that with y times t. So you just take your function and everywhere you see an x, change it to xt. Everywhere you see a y, change it to yt. And if you do that, what has to happen in order for this to be homogeneous of degree 0 is that this new function has to be exactly what it says here, equal to what you had before. In other words, let me put it to you this way. If I change every x to xt and every y to yt and I simplify that thing, the t's have to all disappear. They have to basically cancel out and take you right back to what the function was before you ever introduced the t into it in the first place. Yeah, Matthew.
Is this like when you multiply both sides of an equation, like an algebra by like two or something?
Yeah, it's kind of like you did some algebra to the expression, but then nothing actually happened. Yeah, you can think of it that way. I'm going to show you an example. Actually, I'm going to show you 2 examples. I'm going to show you something that's not homogeneous, and then I'll show you something that is. And then we'll try an example of solving one of these things. So here's an example. If I take the function f of x, y, I just want to kind of look at the function itself for a minute. Let's say it's 3x divided by the quantity 5y plus 2. So we take that function right there. I claim that this function is not homogeneous of degree 0. since. So now I'm gonna try to explain it. Why is this one not homogeneous at degree zero? Well, take a look at what f of xt comma yt would be. In other words, what would happen? What would happen if I actually change every single x to xt and I change every single y to yt? So everywhere I see an x, I'm gonna rewrite it as xt. Everywhere I see a y, I'm gonna rewrite it as yt. So you see what I did here. The question is, after I do that, is it the same as if I just had the original function back again? The original function's right above it here. Are these two things the same?
No, because you have the constant 2 without a t. So
Exactly, that 2 does not have a t with it, so of course algebraically, I'm talking about the algebra now, I cannot cancel those t's. This is not equal to 3x over 5y plus 2, that's exactly right. So the t's have been introduced, but they don't cancel back out. That's my point. Okay? Are we following that? It's just an algebra thing, really. Let me try one more, just so you can kind of see a comparison with another example. It's kind of along the same lines here. What if we had f of x and y? Let's take this example. This time it's going to be equal to x squared minus xy plus 2y squared all over 2x squared plus 3y squared. Let's just try this one for a second. I want you to imagine attaching a t to every single x and to every single y. That's how this works. That's the game we're playing here, right? So this would be, sorry, I was supposed to write a sentence here. This is homogeneous of degree 0 this time. Since this time, if I do f of the quantity xt comma yt, so if I take that expression, and now guys, everywhere I see an x, I'm going to change it to xt, but I'm going to be careful. This x squared becomes the quantity xt squared. And then I have minus the quantity xt times the quantity yt, and then plus 2 times the quantity yt quantity squared on top. And then on the bottom, I'm going to have 2 times the quantity xt squared plus 3 times the quantity yt squared. Yes.
would it be wrong to write the middle expression as x y t squared?
No, that's actually probably the natural thing to do there. If you wanted to do that, that would be totally okay. So my question, actually our question now is, we just introduced all of these t's. Can we get them to cancel out? Because that's what homogeneous of degree 0 means, is we can cancel out the t's. Does that happen here? How can I make that happen? That it? Yeah, you're saying the same thing. I think basically you have t's that can be factored, right? So on the numerator, notice I have every single term has a t squared. And if I pull out a t squared from every single term, then in the brackets here, I get the quantity of x squared minus xy plus 2y squared. And I can do exactly the same thing in the denominator, right? I could take out a t squared down below. And if I do that, I see that I have a 2 with an x squared and then plus a 3 with a y squared also in those brackets. Guys, I want you to think of the t's like weights. Every single x has a weight of 1, and every single y has a weight of 1. And those t's are like weights. And what we're noticing is that the weight here, the weight of this function is balanced on top and on the bottom. There's exactly 2 weights on every term on the top and 2 weights on the bottom as well. And we can cancel these t's, and sure enough, That is f of the original x and y. Exactly, so this one is homogeneous of degree 0. So if we saw a differential equation that was y prime equals this, it would be homogeneous of degree 0. Of course, we should also stop and say, well, wait a minute, was it separable? Was it linear? Was it Bernoulli? Like, we have to go through the usual list of questions because these things can all be mixed together. But certainly, this one is homogeneous of degree 0.
I need to take pictures of the
Are
lecture.
you, me?
Oh, my phone doesn't have enough storage.
Okay, I'll let you guys work on that. Are you helping him?
No,
I suppose I could like,
pictures?
are you asking me to take a picture for you? or-
Yes, we got,
Okay.
yeah, sorry about that.
Is everybody okay? Was there a hand up?
of that,
I'll
or-
do it.
Yeah, Andy?
So if you're looking at a differential equations, what would you like look for? To be like, oh, if you solve any of the three, which one would you go for first?
Well, I usually just go in the order that I learned them. So I first ask
Okay.
myself, is it separable?
I'll text
Then I ask,
them
is it
to me
linear? Then I
at the end of
ask, is it
class.
Bernoulli? And then I ask, is it
All right,
homogeneous
thank
of
you.
degree 0?
But if it's like multiple, right?
It could be. It's
Or
possible.
Which one would you prioritize to solve it?
No preference. You can choose whatever you prefer. There's not really a right answer to that. It's pretty rare that you're gonna see one of these differential equations that fits into multiple categories. It's kind of rare. Let's try one example of this and then we're gonna take a 10-minute break. Okay, so let's do the following example to practice. Oh, I haven't told you how to solve it yet. I get ahead of myself. Like I've said, okay, now we know what a homogeneous differential equation of degree 0 is. It's like, okay, what are we gonna do with it? Okay, so I need to explain that part and then we'll do an example. How about that? Getting ahead of myself. I do that all the time. So here's the deal. For a homogeneous differential equation of degree 0, we use the following change of variables. Now, this is a completely different one than we had before. Remember for the Bernoulli equation, we had this one. Somebody out of the sky wrote this down and it turned out to work. It turns out for the homogeneous differential equations of degree 0, we have to use a different one. And I'm not even going to use a U for this. I'm going to use a different letter just to completely keep it straight. And here's what we're going to use. We're going to replace the y with x times v. Okay, so you're going to want to know this. You will want to know that y is equal to x times v. I'm just going to take one step ahead here because I also know that in these homogeneous differential equations, I see on the left side there will always be a y prime. And so we might as well write down what y prime would be equal to while we're at it. In other words, what is the derivative of this? It's just a product, right? I just take the product. First term times the derivative of the second term plus the second term times the derivative of the first term. And the derivative of x is just 1. So there's y prime right there. So we can write down what y is and what y prime is, and that's what you end up having. So you'll substitute this in on the left side, and on the right side of the original differential equation, everywhere you see a y, you're going to change it to x times v. And magically, what will happen every time is the differential equation becomes separable. Let's try an example to see that. Now I'm ready to do the example to see how that works. Again, this is kind of magic. If you've never seen this before, you would be like, where did that come from? Right. That's exactly what I said when I first saw this type of differential equation. So don't feel like somehow you're missing something, right? This is supposed to just feel like, okay, somebody figured this out long before we were ever here, and it always turns out to work. And so here's an example to practice that on. This one is actually easier because we don't have to do the integrating factors and all of that. It goes pretty quickly. So let's just try this example. let's solve y prime equals y over x plus the square root of the quantity x squared and then minus y squared. Sorry, 16x squared minus y squared, and then that's all over x as well. So this is the example I want to do to show how we solve these homogeneous differential equations. Okay. Again, not a bad idea to ask yourself, is it actually separable? This one's dead in the water right away. You're never going to get an x and a y apart from each other when they're under a radical like that. There's no algebra on the planet that could possibly kind of extract that out. So it's not separable. It's obviously not linear anytime I see a y squared in it. And it's not even close to the form of the Bernoulli equation either. So I like to go through that mental check. It's not separable. It's not linear. It's not Bernoulli. So what's the fourth type of differential equation that we've learned about? It's homogeneous differential equations of degree 0. So I ask myself, if I take this f of x and y right here, that's on the right-hand side, if I replace every single x with xt and every single y with yt, will the t's just cancel back out again like they did on this example here? Well, you can see it right here. If I have y over x and I put a t next to the y and next to the x, those t's will cancel. And if I put t's next to the x's that are underneath this radical, notice that that's actually going to give me t squared on both terms. And when I yank that out of the radical, it becomes just t again, which cancels with the t that would be on the bottom here. So this is homogeneous of degree 0. Homogeneous of degree 0. I'm not going to write that one all out. I will just say, for those of you who are feeling ambitious and just want to make 100% sure I'm not going too fast here, feel free to check that by writing it out. I won't write it out this time though. I'm just going to move on to the process that we're going to use. So now we do the change of variables. Let's just take a couple more minutes, then we'll be done. This goes quickly. So the y prime on the left, I just end up having, I just write that as x v prime plus v, right? And what do I do on the right-hand side? On the right-hand side, everywhere I have a y, I change it to xv, right? Y is equal to xv. So what we'll have here is xv over x plus the square root of 16x squared minus y squared, but y squared is x squared v squared, and that's all over x. And now I can cancel these x's. Right? And notice now I have a v here and a v here. So I can also cancel those, because there's one on both sides of the equation. And if you believe me that this is going to become separable, you might remember from my video notes last week that I always recommend with separable equations that you take this derivative and write it in the, the dy over dx notation, or in this case, dv over dx, okay? And the right-hand side, oh, I forgot, I didn't fully simplify this, did I? What do we have happening over here? These two x squareds, right, they can be factored, pulled out of the radical, and then canceled with the x on the bottom. Actually, all that's left there is the square root of 16 minus v squared. Nothing else survives. Nothing else is going to survive that. The x is completely canceled. Just looking separable. Look pretty separable to everybody. I can get all the v's on one side, right? I can move this radical underneath the dv. So dv divided by the quantity of the square root of 16 minus v squared. On the other side, I could put the dx over x. Right? basically you have to flip this over, right? The dx that was on the bottom now goes to the top, the x that was on top now goes to the bottom. And we have separated the x's and the v's, and I'm ready to go back to how we solve separable differential equations. We're gonna integrate both sides. Is everybody with me? This kind of goes, I mean, you solved this integral by doing a trig substitution. Maybe some of you remember that. Kind of goes above and beyond what I will generally ask you to do. In fact, you'll find this integral in the table of integrals that I'll always be just giving you. Wouldn't worry about it too much. I'll just tell you right now what the answer is. It's the arc sine of the quantity v over 4. Okay, so again, that is coming from calculus. It's in any standard table of integrals. We'll go ahead and assume that we can use that. The right-hand side, of course, we should know the antiderivative of 1 over x dx. That's the natural log of the absolute value of x with a big plus c on the end of it. And so I've integrated both sides. Am I done? What should I maybe do next? Say again? Okay, we should try to get back in terms of the original variable, which was y. And I have a way of doing that. I can basically replace v with y over x. And I would recommend that we do that. So let's do that. This becomes the arc sine of y over, and it'll be a 4x because there was a 4 on the bottom. And then this is equal to the natural log of the absolute value of x plus c. I like it. And now am I done? Technically, this is not wrong. I mean, I could leave it like this, but this is what you would refer to as an implicit solution. Remember, if possible, what did we say earlier? If possible, we should try to explicitly solve for y. Can somebody tell me how I'm going to yank that y out of there and get it by itself, isolating it?
Take the sine of both sides.
Take the sine of both sides because that will, of course, cancel the arc sine. So if I do that, if I take the sine of both sides, y divided by 4x will now be equal to the sine of this whole quantity. Guys, parentheses are your friend. Make sure you use them because this plus c needs to be inside of those braces. It shouldn't be just lagging on the end. And I'm almost done now. The last thing I would recommend is that we actually solve for y by moving the 4x to the other side. So 4x times the sine of the quantity of the natural log of x, absolute value of x plus c. And that looks like a pretty good final answer. Wow. A change of variables approach has taken this homogeneous differential equation. I mean, it's pretty messy equation, right? But we've converted it into a separable one that we can solve with simple integration. Basically how this works. Guys, I could take the next 14 weeks of the semester and just do a part C and a D and an E and an F. And I could show you more and more types of differential equations. And here's the trick for this one. And here's the trick for that one. And here's the trick for the next one and so on. And we could do that. And, you know, I've only done 2 so far, and I get sense we're going to get bored with it pretty quickly. It's going to involve a lot of memorization. It's not going to help us to grow sort of mathematically very well. It's just I could just teach a cookbook class, right? That's basically, here's all these differential equations, and here's the trick for solving them. I think it was worth it to show you this change of variables technique because it's strong, it's powerful, and it is very useful. But I think that even in 1 hour now, it's already kind of seen its time, right? And we've kind of got the hang of this. We have the idea behind this. So I have a much better idea. Instead of spending 14 more weeks just giving you this differential equation and this technique for solving it and going like that back and forth forever and boring everybody to tears with way too much to try to memorize, I would like to aim a little bit higher in terms of the sophistication of what we're going to do in this semester. What I would like to do instead of this kind of cookbook recipe thing is teach you an entire different side of math, a toolbox that you may or may not have seen much of before, especially if you've been focused mostly on calculus. I would like to teach you all about linear algebra. Actually, you guys all know that I wrote the book on this. I have a co-author who is a specialist in differential equations, so he kind of took care of that part of it. I'm kind of the linear algebra guy. I actually am an algebraist. It's what I did my PhD in. It's the kind of math that I love the most. So if you think I was like enjoying this part of the material, wait till you see the linear algebra side of it. I love that even more. We're going to spend about 10 weeks. Oh my gosh, 10 weeks mastering linear algebra, both for its own sake, because it is actually very interesting and very powerful in its own right. But then, as I said, I love teaching the class because round about November, we're going to go back to the differential equations again and use this powerful tool that we're going to be developing called linear algebra. That is a much more, I think, lofty approach to this material. A lot of universities don't do it. Let me just be very clear. There's a lot of universities who say you're going to take a straight differential equations class and then a straight linear algebra class, and they never talk to each other. They never interact, and they try to somehow fill in those little gaps between them. It's hard to do that, right? But in a class like this, we sort of have the structure built into the syllabus and the time available to do it, to sort of merge these two things together is one of the most beautiful things I've ever seen in math. And I've done a lot of math in my life. So I'm excited to share it with you. What we're going to do is take a 10-minute break right now. After we take a little break, I am going to start chapter 2, which is the start of the linear algebra. We're going to kind of just get our feet wet with it a little bit today, and then we'll move further into it when we get to Thursday. So let's take 10 minutes. It's already about 3:20, so I'm guessing at about 3:30, I'll be picking back up again, and we'll do that. I'll see you in a few minutes.
I was actually wondering for the homogeneous degree of 0, right?
Yeah.
Why can't you use it when you have the non the xt y because then y and this will always kind of work, right?
For a
Because
homogeneous, yes.
or I mean like this equation will always kind of work because no matter what number y is.
You can try to use this substitution for any differential equation, but the key is you want to turn it into a separate one.
Okay. If it's not
If it's not homogeneous at degree 0, that change of variables, although it's not illegal to use it, it won't work.
it was
It will turn it into a separate.
Okay, then I was gonna, cause I was like, no matter what, even if you multiply x by anything, some random thing, you can always kind of manipulate it to get to y.
That's right.
It's like a really basic algebra question.
That's good.
Why is 15 minus 30? Why is it not 8 on the table?
Oh, you could put it in there if you wanted to, it wouldn't be wrong, but it's always better for them. Like, you don't always, you don't, well, it's not only better, it's actually, like, you can't have like the x down here, if I wanted to integrate by x squared plus y. You can't just have, just occasionally, and calculus would work. It's gotta be, you gotta put those things on. Oh, yes.
Are we just saying?
Nick.
Oh, you're emailing it to me?
Yeah. Is that okay?
End of class.
Oh, geez, that was tough times.
I figured I'd like take your email back, just so that like I could do it like on the night.
Okay, well,
We'll always be doing something, Tuesday or Thursday, and then we'll be doing something.
Okay, so basically.
Oh, are you really?
Yeah, so I won't be able.
oh, my email is not working either, so you can just do text.
No, I don't think so.
I said like.
Yeah, cancel email. Hey, Dr. Annette?
One second, I need to take a break here.
Dr. Annette?
Email by Canvas at 1.9.
Canvas?
Yeah.
All right. Oh, well, can you do it end of class? The shot. Or you can do the rest later.
I'll do the rest later. I'm just, it's been a while since I've actually sent anything, so I should probably like just double check stuff.
Are you a student in my class?
Yeah,
Oh, okay, what was your name again? Oh, that's right, okay, I'm sorry, I thought you were an assistant or something, okay, I got it now, okay, thank you.
Hey, did you ever provide extra credit on exams before? Alright.
I just asked. It's not going to be something on the.
So, you know, like a.
Not to make it easier. That's, the majority of the box.
It's like, I was just like, like all so the total line, yeah, and he was like. I feel bad, you are, I feel you like,
Thank you. Yeah, I know.
I had like 6 minutes left. Usually you have something like that. And so
And then I take a break and I come back. And you can come in sooner, whatever's easier for you, but I'll be down in my office, but I'll. It sounds good. Oh. Yeah, it's down in the basement of this building. I think. I know.
For now. I know. So what do you already got? I it's the worst. I'll be serious. Are like freezing. I think. And so I remember.
Are you ready to?
Yeah, I'm gonna start here in a second. I'm gonna go ahead and get started again. I only have about 20 minutes, so we won't get too far much further in. I just want to remind you, this is the homework that's due tonight. Make sure you do all of these required problems. My grader will be randomly sort of choosing which ones to grade in detail. You'll also get some points just for turning it in, just working out every problem regardless of the correctness of it, but my grader will choose some of them to grade. He'll only choose from the required list. He won't look into any of the recommended ones. But try to get that done. And of course, I'm happy to help you during my office hours with any of those. On the true false items, which are kind of sometimes at the beginnings of these sections, please don't just write true or false on each one. What I would like is a brief, I mean, very brief, one line, maybe two, if you really want to stretch it, little reason for why you're saying it's true, or why maybe there's something wrong with the statement. So you mentioned what's wrong with it. Why is it false, or why is it true? It doesn't need to be an essay or anything real long. But if you just write true or false and my grader happens to pick that problem and all that's all you've written, you won't get any credit for it. So make sure it's just a brief little idea about why you're saying it's true or false. So that's for tonight. And then don't forget, there is one to look at for Thursday as well. What I wanted to do though is go to this pages section of my Canvas page, because this is where I have all the videos for the class posted. There's going to be some review session videos and so on. And I'll put all of the class lectures in this folder. It's like the one I'm recording right now. I'll put it in there, like by tonight, it should be up in case you want to review anything from today. But I also wanted to point out the additional videos folder here. So the one that, or the link here, it's at the very top. This is a bunch of YouTubes that I've made, right? And somewhere down here, here's the one I was talking about earlier today where I'm highlighting it. What does it say there? It says converting a Bernoulli equation to a differential equation, a linear differential equation. And it says it's 3 minutes. So if you want to fill in that little gap where I sort of said, oh, if you do this change of variables, the Bernoulli equation becomes linear. I actually show the math of that. You're probably not going to need it in terms of like for this class on a test or something, but some people really like to fill in all those gaps for themselves. So you can always watch that little clip. Just be sure to click the like button after you watched it, to make sure that I get credit for that. I'm not making any money off of my YouTube channel, I promise. But still, I would love it if you would like any videos that you see here. None of this is required. None of these videos. This is just extra stuff. Now, sometimes I might ask you to watch something. You know, especially if we get behind and I need to kind of catch up a little bit, I might assign you to take some notes on some of these videos. But as of right now, I don't have anything in mind as far as that goes. I just wanted you to know that this is here as extra resources for you. Okay, so just wanted to point that out. I guess I'm going to go ahead and mute that screen for now. As advertised, we are going to take a big hiatus from differential equations now and start talking about linear algebra, particularly as it will be a tool for differential equations. But, you know, how many of you have seen matrices before? Raise your hand. Have you seen matrices? A lot of you have at least seen them, which is great. I am going to try to be fairly thorough in reviewing some things here. It's going to sound a little bit, you know, as exciting as I like to make linear algebra out to be. We sort of have to start off with a whole laundry list of definitions. So bear with me for 20 minutes here as we kind of wrap up today. I'm just gonna kind of give you the bare bones intro to this, and then we'll start really getting into it more on Thursday, I would say. Okay, so there's gonna be a bunch of definitions here. I'm gonna start with just what is the definition of an equation. Right, it says systems of equations. So let's make a definition here just to kind of start off chapter 2. It's always nice to get that first chapter under our belt. Now we're kind of moving into the heart of the course here. So here's the definition. A linear equation. A linear equation, I'll underline that. It has the form. And so here we go. It's going to be A1 times X1 plus A2 times X2, and we go dot, dot, dot up to AN times XN equals B. So this is kind of a notationally heavy expression, but just to be really clear here, these X's, I'll call them X sub I, those are generally kind of understood to be the unknowns. They might represent some physical quantity in a real world problem, right, from one of the sciences. Those are the unknowns that you hopefully would like to solve for. But you might also have other constants like A sub i's and b's. These are just constants. So those would be given. Those would be numbers that we already know ahead of time. Okay, so that's a linear equation. And along with that, I'm going to make a sort of a definition that goes hand in hand with that. Part and parcel with the linear equation would be something called a linear system. So a linear system, make another definition, a linear system of equations is a collection of linear equations. Okay, so a linear system is just a collection of linear equations, just a bunch of them. Let me just write down an example. This is not a terribly hard concept, and I'm sure you kind of probably looked at this kind of thing somewhere in the past, but let's just write down an example here. Suppose I had negative 3x plus 2y plus z minus w equals 5. And then maybe I have 2x plus 2z equals 3. And then maybe I have negative y plus 5z plus 2w equals 0. Maybe I have that collection of 3 linear equations. That's an example of a linear system. Here I've used x, y, z, and w for the unknowns rather than x1, x2, x3, and so on. If I have just a small collection of unknowns, I certainly can use whatever letters I want to denote those unknowns. But ultimately, guys, the goal of, well, one of the goals of chapter 2 is to solve linear systems. So these are not differential equations, right? There's no derivatives here. These are just linear equations, and our goal would be to solve these systems of linear equations. I'm going to add something though here to this. Sorry, take off my little exclamation point for a second. I would like to solve linear systems, but I need to add a little proviso, which says if possible. Because it is possible to have a linear system that you cannot solve for the unknowns. That is actually possible, and it can be hard to tell just by glancing at it. It can be hard to tell whether or not it's going to be a system that has solutions or not. By the way, that gives me another definition to write down. Sorry, a lot of definitions here. I apologize for that. But it's just starting a new topic, so we kind of have to write some things down. So how do I want to phrase this? A linear system, this is a definition. A linear system with at least one solution is called consistent. Right, so if there's at least one solution to our system of equations, if there's one choice of X, Y, Z, and W that we can plug into all the equations and it works, then we're gonna call it consistent. Otherwise, I'll add a little bit more here. Otherwise, it is inconsistent. So this very definition is sort of already acknowledging that it's possible to have linear systems that don't have any solutions. That is actually possible. I bet you could all think of one. You know, if I gave you x plus y equals 2 and x plus y equals 3, that was my linear system, and I ask you to solve for x and y, right? You're probably going to realize that there's no values of x and y that satisfy all of these equations. This system is inconsistent. So that's an example of an inconsistent system, and you know, in that case, there's not much more you can do, right? You're just gonna have to accept that and move on. If the linear system is consistent, then we often will want to actually solve it. We would like to find what are those solutions to that system. And that's going to be largely what we're going to be doing in the next couple of classes. We're going to learn the procedure for solving these linear systems. Okay? In other words, we're going to try to tackle this goal here. Before I get into that, though, I want to point out that if we would like to study these systems of equations, the main tool that we're going to use to do that is the so-called matrix. So that's the other part of what chapter 2 is about, matrices. So we will use matrices, that's the plural of the word matrix. We will use matrices to study linear systems. When I have a bunch of equations I'd like to try to solve, we'll often be using matrices to study them. Well, I gotta be careful. I better give the definition of a matrix here. I know a lot of you said you've already seen this before, but I am going to, at least for the record, write it down one time here for you. I usually will refer to a matrix by its size. So the size of a matrix is usually denoted with 2 letters, M and N. So an M by N matrix. This is the word I'm defining. I'm going to usually use a capital letter to denote my matrix. I often will start at the beginning of the alphabet. So we'll start with the capital A here. This is an array. It is an array of numbers. It could be numbers or functions. It's actually possible to fill out this array, not with numbers, but with functions instead. Arranged in M rows and N columns. Right. So we can arrange it. So the rows, guys, of course, make sure everybody's clear. Those are the horizontal slices that go through the array. The columns go up and down vertically. If you chop through the array of numbers or functions, those give you the columns. So it's some kind of a rectangular shaped array with M rows and N columns. We could write down an example of a matrix here in case this isn't totally clear. I'll just write down one quick example. Maybe capital A is the matrix whose first row is -3, 2, 1, and -1. And maybe the second row is 2, 0, 2, 0. And the third row is 0, -1, 5, and 2. So this is an array of numbers in this case. So it's a matrix of numbers. Can somebody tell me the size of this matrix? What's the M and the N? Let's get this very carefully. How many rows does this matrix have? 3 rows, right? The rows is the M values. That's the one we write down first. So there's 3 rows. And how many columns are there? 4. So this is 3 by 4. I sometimes like to just put that here just to kind of grab your attention with that, that's the size of the matrix. Some people will refer to that as the dimensions of the matrix. I personally don't like that word as much because it turns out that dimension has a different meaning that we're gonna see later in the course, so I'd rather focus on using the word size here. Does anybody know where I got this matrix from? Did I just pull it out of the sky or is it somewhere? Yeah. If we go back to the linear system from a few minutes ago and we kind of look at what the numbers are that are in front of the unknowns, that's exactly what I have there, right? The -3, the 2, the 1, and the -1, right? 2, 0, 2, 0. It's exactly right. This is actually what is called, another definition here, guys. This is called the matrix of coefficients for the linear system above. Right, it's the matrix of coefficients for that linear system. And this is what I'm talking about, that we're going to use matrices to study linear systems, right? The first thing we're going to do is take our linear system and rewrite the matrix that goes with it. The only thing is here though, guys, with this matrix, we have lost track of the numbers that are on the far right-hand sides of these equal signs. And let's say I want to keep track of those. We can do that as well. We can use something called the augmented matrix. Let me make another definition here. The augmented matrix this is all very simple stuff, but in the homework that you're going to be doing, this is like 3 assignments from now, so a ways ahead, but they're going to give you a linear system and ask you, what's the matrix of coefficients? What's the augmented matrix, and so on. This is usually written as A#. So augmented matrix is emphasizing that what we're hoping to do here, guys, is keep track of the right-hand side. So this includes the right sides of the equations. So again, I will just very briefly write down this example. In this case, the A# would just be, -3, 2, 1, -1, and then there's a 5 over here, right? And then the second row is 2, 0, 2, 0, but now we're going to keep track of the 3. And then the last row is 0, -1, 5, 2, and then we have a 0. Now, this is very important, guys. We actually need to, well, we don't need to, we should, to keep this clear for ourselves, use a bar inside of this augmented matrix to sort of separate off the numbers that are on the right-hand sides of the equal sign. Actually, in the previous version of this book, we did not do that in the book, and it was really making it harder to understand. So I have to emphasize that this will really help you. It's not wrong to leave off the bar, but I'm pretty much going to red pen you for sure if you don't have that bar on there. We really need to try to show that, okay? This set of numbers here on the right-hand side, right? This is, well, just this right-hand side column. It is in fact a matrix in itself, right? It is a 3x1 matrix, but you might even recognize it under a more familiar name. Since it's only a single column of slots of numbers, you probably would be more comfortable just referring to this as a vector. You would have seen it in Calc 3, for example. So this is what is often called the right-hand side vector. Sorry, I'm kind of going quickly just to get a few of these terms in. You're going to see that in the book as well. It's not a big deal. It's just kind of common sense that that's what that is. But given any linear system of equations, you can talk about the matrix of coefficients. You can talk about the right-hand side vector. You can talk about the augmented matrix. These are all very simple things. You can write them down without really showing any work. You just sort of present, here's what everything is. Okay, it's pretty simple. The last thing I'll do for today, and we'll pick this up on Thursday, I'm just going to start making a list. So give me just 2 minutes to finish this up. But essentially, what we're gonna need to talk about more next time are some operations on matrices. So we're going to be doing things with these matrices. Obviously, they're not just going to be dead sets of numbers or arrays of numbers. We're gonna actually do stuff with them. The first thing we will want to be able to do with these matrices is something called a transpose. So I'll just explain again, this is a very simple idea, but I'll just very briefly talk about it. What you're doing when you transpose the matrix is, first of all, you're going to write it this way, A with sort of a, that this is not literally an exponent. It's just a notation for the transpose of A. And what you're going to do here, guys, is this is a new matrix whose size is n by m. It is an n by m matrix with rows and columns swapped. What I mean is you just sort of switch the rows and the columns. Okay, so in our example, just put this one example. If we take the matrix A up there and we decide we want to transpose it, the first row will then get written as a column instead. So -3, 2, 1, and -1. And the second row will then be written as a column as well, the second column, and then the third row gets written down as the third column. And you can see if you do that, you're literally just mindlessly switching rows and columns. There's not a lot of depth to that. You can see that the size of the matrix has changed. Right, the original matrix was 3 by 4, and now this matrix is what size? 4 by 3, right? So it's a different size matrix. Now, some of you may be sitting there wondering, well, why on earth would you ever do this? I mean, after all, if you tried to write down a linear system that goes with this matrix, it wouldn't look anything at all like the original system here. In fact, it wouldn't have the same number of unknowns. It wouldn't have the same number of equations. It's kind of like, who would do this? Like, why would you do this? Turns out the transpose is a really, really powerful tool in linear algebra. It comes up in a lot of important mathematical applications, statistics and data science. Those places see lots of this kind of action going on. So it's something good to be aware of. But I won't, in 1 minute that I have left, have time to really go into much detail about that right now. Just a second, Matthew, I want to get something else in before I absolutely am out of time. I'm just going to tell you where we're going to pick up on Thursday. There's 2 more operations that we're going to discuss. The number 2 item here is just calculus. That actually is more relevant when your matrix is an array of functions. Because when you have functions inside your matrix, of course, what you can do is take derivatives, take integrals, take limits, all those things that you associate with calculus. You can do them with a matrix, right? And I could ask you to integrate a matrix or differentiate a matrix. Of course, what you're going to do is you're just going to do it for each slot of the matrix, right? If I ask you to integrate this matrix, you're literally going to go through each of the 12 entries and just do an integral. That's like giving you 12 homework problems, but I tell you it's only 1. But if you find the integral of that matrix, that's what you have to do. So I'll come back and talk about that next time. And then finally, the third one, which I'll also talk about next time, is algebra. And by this, I mean adding 2 matrices, subtracting 2 matrices, multiplying 2 matrices. How many of you have seen matrix multiplication before? That one's a little quirky, right? It's not like what you would expect. It's a little bit of a surprise. I always like to end class by kind of like giving you a reason to come back, like there's something exciting or different or weird gonna happen next time, so that's it. On Thursday, I will talk about the weird way that we multiply matrices together, and we'll pick up our conversation from there. Guys, thanks for a great day today. I will see you all
Oh.
on
What's your name?
Thursday.
Oh, Kim, you can send the pictures to me. Let me connect to the internet first.